This video is part of the MCAT chemistry video course. Subscribe if you'd like notifications about the release of new videos, and please visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we'll go over chemical formulas and chemical equations. So we'll talk about the different types of chemical formulas, and then how to find the percent mass, and then how to balance chemical equations. The molecular formula tells you which elements and how many of each element are in a molecule. So if you look at the first one, the C6H12O6, so in that molecule, we have 6 carbons, 12 hydrogens, and 6 oxygens. And then the next one would be 4 phosphorus atoms and then 10 oxygens. And then on the third one, we have 10 carbons and 22 hydrogens. Molecular formulas are used for both covalent molecules and ionic molecules. So if we had an ionic molecule like NaCl, you would just use the exact same approach where you have 1 sodium and then 1 chlorine. The empirical formula just shows you the smallest whole number ratio of all of the elements in a molecule. So if we take the first thing that we did, which was C6H12O6, and then take the empirical formula of that, we would just be looking at what's the smallest ratio of those atoms. If you look at those numbers, you can see that for every 1 carbon, there are 12 hydrogens, and then for every 1 carbon, there is 1 oxygen. So then that gives us the empirical formula where we have 1 carbon, 2 hydrogens, and 1 oxygen, because those are the smallest ratios of those atoms. So that would be a 1 to 2 to 1 ratio of those 3 atoms, which you can find this by just finding a common denominator between those numbers and then dividing each number by those. So for that molecule, the common denominator would be 6, the largest common denominator, and then that gives you the 1 to 2 to 1 ratio. And if you did the same thing with the next molecule, the P4O10, and divide each of those numbers by 2, then you get your smallest ratios, which would be a 2 to 5 ratio of phosphorus to oxygen. And then the next one, you have the same common denominator of 2, so you divide those numbers by 2, and you get a 5 to 11 ratio of those atoms in that molecule. Now we'll talk about molecular mass, and molecular mass is simply just the mass of a molecule, and it's measured in Daltons or AMU, which is atomic mass units, and that's just a super small unit of mass. You find this by using the periodic table and then finding the masses of the individual elements that are in your molecule. And then you need to multiply those masses by the subscript for those elements. So pull up a periodic table and then look at the masses for these elements. And I'm going to do rounding for these because on the MCAT you definitely always want to be rounding. So the mass of 1 carbon would be about 12. And there are 6 carbons, so you're going to do 12 times 6. And then you're going to do the same thing with each element and then add all of those together. So hydrogen has a mass of about 1, and there are 12 hydrogens. And then oxygen has a mass of about 16, and there are 6 oxygens. So those numbers come out to be 72 plus 12 plus 96, which total gives you about 180. So with rounding, we ended up with about 180 atomic mass units, or Daltons. We'll do one more with water. So water has hydrogen, which is round that mass to about 1. So 1 times 2 plus the 16 for water, and there's only 1 water, so we don't multiply that by anything, which gives you a total of about 18 atomic mass units, or 18 Daltons. The percent mass is just what percent of a molecule's mass does a particular element contribute. So we'll just use our C6H12O6 molecule for an example here. And now we're just going to look for the percent mass of carbon from C6H12O6. In carbon, remember there were 6 carbons. So we do carbon's atomic mass times 6 to give us 72. So of the 180 atomic mass units, 72 of that is from carbon. So then we'll do 72 divided by 180, which is equal to 0.4, which would be 40%. Now the same thing for hydrogen. Hydrogen has a mass of about 1. There are 12 hydrogens, so total hydrogen contributes about 12 AMUs to the total mass of that molecule. And we'll do 12 divided by 180, which gives you about 6.6%. Now for oxygen, there are 6 of them, and 6 times 16 will get you about 96. So 96 divided by 180 gets you about 53.3%. And if you add up all of those percents, you will get at 100%, which you should always do if you were to have all the percent masses of all of the elements from a particular molecule. The last thing we'll do is look at balancing chemical equations. And when you balance chemical equations, the whole reason you have to do it is because of the conservation of matter, which basically is just telling us that the amount of each atom must be equal on each side of the chemical reaction, and that's for each element. So the amount of carbons on one side has to be equal to the amount of carbons on the other side, and so on. So for every single element, the amount of that element has to be equal on each side. Most of the problems on the MCAT, you're not going to have any process. The balancing is going to be pretty straightforward. But here is a process you can do that you can use in case you run across one that's just a little bit harder. First, you want to write out each element that you have for the reaction. So we have carbon, we have hydrogen, and we have oxygen. And you're going to write that on both sides. So carbon, hydrogen, oxygen. And then write the amount that you're starting with when your reaction is not balanced. So we have 6 carbons on the left, we have 12 hydrogens on the left, and we have 8 oxygens on the left. And then on the right, we have 1 carbon, we have 2 hydrogens, and we have 3 oxygens. So now we're going to balance these by changing the numbers that go in front or on the left side of your molecules. So if you look at the C6H12, the numbers that go right there. Make sure you're never changing the subscripts, because if you change the subscript, what you're saying is that the structure of that molecule is changing, and that is not up to us. We cannot decide. We can't decide what the structures of these molecules are or their chemical makeup. We can only decide how many of them react. So starting with carbon, the first thing that we can do is balance out the carbons. So on the right side, we only have 1, but we need 6. So just start with the simplest move and then see where that takes you. So we're going to put a 6 in front of the CO2, and then now we're going to adjust our numbers. So instead of 1 carbon, we now have 6 carbons. But we also changed the number of oxygens. So instead of 3 oxygens, now we have 12 from the CO2 and the 1 from the H2O. So now we have a total of 13 oxygens. Our carbons are now equal, so just go to the very next atom and see what you can do with that. So we need to adjust the number of hydrogens on the right. We only have 2, but we need 12, so we can add a 6 to the H2O to give us 12 hydrogens on the right. But that has now changed our oxygen numbers again. So now we need to adjust our oxygen numbers. So we have 6 oxygen from H2O, and then we have 12 from CO2. So we have a total of 18 oxygen atoms on the right. And our last element, which is now the only one that's unbalanced, is oxygen. And we need more oxygens on the left side. And you do have 2 ways that you could increase the number of oxygens. You could do numbers in front of the C6H12O6, or you can put a number in front of O2. Pretty clear here, you're going to want to put the number in front of the O2 so that you don't change the amount of the other elements that you have. And you can see that we need 10 more oxygen atoms. So we have 1 O2. So if we need 10 more oxygen atoms, that means we're going to need 5 more O2s. So we're starting with 1. So if we had 5 more, we would have 6 O2s. And if we add up the oxygens that we now have on the left, there are 12 from the 6 O2s and then 6 from the other molecule, which that would give you a total of 18 oxygens. And now you're totally balanced for this atom, for this reaction. And now that we have a balanced reaction, it's really important to point out that, for one, these numbers, the numbers that we wrote in front, those are called the coefficients. And the coefficients tell you the ratio of the reactants and products in this reaction. So what it's saying is that, let's say, if we know we have 1 of this molecule here, then we would have 6 of all the other molecules, because this is telling us the ratio. Where if we had 2 of this molecule on the left, then we'd have to have 12 of all of the other molecules. What they do not tell you, and this is going to come up more in stoichiometry, they do not tell you the actual amount of moles that you're working with. So sometimes people get mixed up where they have a problem where they're working with like 10 grams of some substance. And then you need to use that number of grams to find the number of moles that you have. And we'll talk about how to do that in the next video. What you don't want to do, and what some people do, is they look at the coefficient and then they'll say, oh, because that coefficient is 1, I have 1 mole of that substance. And that's not what it is. The coefficient is just telling you the ratio of the products and reactants in the particular reaction. We'll do one more for some additional practice, and I'd recommend just pause the video and see if you can just replicate the process that we just did. And we'll start by just writing out all of our elements and the amount of each. So there's 3 sodiums on the left. Now we run into something that is pretty useful to know. If you see something like PO4 and it shows up on both sides, you can just keep that whole thing together. It'll make it go a lot smoother. And one way to recognize when you can do this is to have your polyatomic ions memorized. So phosphate is a super common polyatomic ion, and those will be covered more in solubility chapters. But phosphate's a really popular one. So if you spot a polyatomic ion, see if you can find it on both sides, and then that's going to make the balancing way easier. So there's 1 phosphate on the left, and now for magnesium, there's 1 magnesium, and then there are 2 chlorines. And on the right side, we have 1 sodium, 2 phosphates, 3 magnesiums, and 1 chlorine. Just start with your top atom. So we need 3 sodiums on the right, so we'll add that coefficient to give us 3. That changes the number of chlorines on the right side to 3 as well. And then now for the second atom, for the phosphate groups, we need 2 phosphates on the left, so we'll put that coefficient there, which changes the phosphate on the left and the sodium on the left. So let's go back and just rebalance our sodiums. So instead of 3 NaCl's, we're going to need 6. And then that will change our chlorines as well to 6. So now our sodium and phosphate are balanced, and then we'll balance the magnesium now. We need 3 magnesiums on the left, so we'll put that there, changes the magnesium, and that changes the chlorine to 6, which just happens to balance out both of our final 2 elements. So there is your balance equation for this one. So just give this method a try, just so you have it as a tool in case you run across one of a harder balancing question on the test.